So I'm Mark Jerrum. I'm currently Professor of Mathematics at Queen Mary University of London. So I did my undergraduate degree in mathematics at Cambridge. So these were fairly early days of computing. Things were quite primitive. And after that, the BSc in mathematics, I'd like to stay on at Cambridge. So I did what was then called the Diploma in Computer Science, which was, we would call it an MSc. And so I enjoyed that. But part of it, there was a module on this relatively recent aspect of theoretical computer science, namely computational complexity, which was at that point in its early days. So I wanted to, and more generally, actually, theoretical computer science. At that stage, I had a more general interest. But Cambridge wasn't the place to pursue that interest at the time. So in order to do a PhD, I came to Edinburgh, which was very well known, even at that point, for its work in theoretical computer science, not mainly of the kind that I was eventually going to end up in, but nevertheless very strong. And so that's how I got into computer science, made the transfer from mathematics, but not at that point specifically interested in my final interest, which was computational complexity and analysis of algorithms. But there was a certain professor here, Leslie Valiant, who was lecturing undergraduate course, final year undergraduate course on this topic, and it interested me greatly. And I signed up to do a PhD with him as advisor. So at school, I was certainly interested in mathematics, and it was something I was good at. I guess that's the main reason that I went on to study at university. Actually, school maths doesn't give you a very good introduction to what university mathematics is like. But when you start studying it at university level, you start to appreciate the beauty of it and the beauty of the patterns. And so I was hooked. I don't know how the interest in computing. I guess at that stage, computer programming was a slightly exotic activity, and that interested me. And then I came to realize that you could put these two things together, that a lot was going on in computer science needed a mathematical foundation. And so it was all vague in my head at that point, but nevertheless, I decided to pursue this further at a research level. In practical computer science, we want to write programs. We want those programs to be correct, behave as we want them to, and we also want them to be efficient. And this is founded on a mathematical basis. So, for example, the correctness of computer programs rests on a logical foundation. So people with an interest in mathematical logic would like to apply that knowledge to the correctness issue in computer science. I, on the other hand, I'm interested in the efficiency issue. So however fast your computers get, you still need to design efficient algorithms, particularly with the scale of data that we see today. We need efficient algorithms to cope with the scale of computing. And the design and analysis of these algorithms, it again rests on mathematical foundations, but of a different sort. So in my case, founded on on combinatorics and probability theory, and to a certain extent logic. So in both of those aspects, practical computer science does rest on some mathematical foundations. Now, at Edinburgh at the time, the emphasis was on this logical, the correctness issue. This theoretical computer science in the European sense, whereas I was interested in the minority interest, which was being pursued in the States principally, which was interested in studying algorithms as the fundamental object of study, and in the mathematics that is useful for designing and analyzing these efficient algorithms. So that is a good question. Up to now, I should maybe preface this by saying that the word algorithms has been hijacked by the media, and it's applied in a very narrow sense to large language models and neural networks and this kind of stuff, rather than the historical perspective, which is of algorithms geared to specific tasks and with precise specifications, and which lend themselves to a more mathematical form of analysis. So I think algorithms as used currently is a much more focused term than it should be. So it's a much wider scope. So the sort of things that I look at and my colleagues look at, because we are analyzing mathematically, tend to be for problems which can be specified precisely, and for which a mathematical analysis is possible. So these relate to real life questions. So if you have a complex organization, you want to optimize something. Maybe you have a distribution network and you want to optimize the siting of warehouses and the distribution routes and everything. But this is a problem with a precise specification, and you can ask what's the fastest algorithm that's going to achieve an adequate solution. So up to now, I would say this topic is geared to the analysis of these rigorously definable questions. Now, obviously, we have algorithms in the modern sense, and I'm not sure at this stage what the traditional theory of computational complexity in algorithms is going to have to say about those. So that's a point which at the moment really is not easy to answer. So the computational complexity theory and analysis of algorithms at its start, it was it was coming from the direction of logic. So there were certain things. So there was recursion theory, which was studied in logic, and that naturally led on to a quantified version. And because it's coming from logic, it tended to focus on yes/no questions, so or decision problems. And a little bit after that, in order to fit this theory better to the real world, which dealt with what's the best way of doing something, it then went on to look at optimization problem. What's the most efficient way of visiting all of these sites? So the traveling salesman problem, or what's the most efficient distribution network? However, if we start from the point of view of mathematics, a lot of the things that we want to compute they're not decision problems, they're not optimization problems, they're sums, they're integrals. So if we were coming to this subject from the point of view of mathematics, it would be very natural to look not just at decision and optimization problems, but also counting and sampling. And I include there infinite sums, so also integrating and computing the volume of things. So that was a natural direction to go in. And actually, in Edinburgh in the late 70s and early 80s, this direction was being pioneered by my research supervisor, Leslie Valiant. It interested me probably because of the methods that are employed. So quite a lot of it has been, up to now, based on certain mathematical objects called Markov chains, which is something that comes from the area of probability theory. And so this is where computer science has had a big impact actually on mathematics, because Markov chains, whatever they are, were extensively studied before in mathematics, but the results were of the form, what happens eventually? What you run this probabilistic system and what happens to it in the limit as time goes to infinity. But in computer science, you're not interested so much in what happens as time goes to infinity, but what happens within a specified amount of time, because you want an efficient algorithm. So this led to a renaissance of study in Markov chain style mathematics, and it took it in a different direction, which was, whereas before it was about asymptotics, or by which I mean what happens eventually, into quantitative. So how long do I have to wait before some desirable result is obtained? So that had a big impact on that area of mathematics, and that interested me. And I'm also interested in the connections with statistical physics, because people in statistical physics are interested in these probabilistic systems, which are composed of very simple units, which interact, and then they have a complex global behavior. And you would like that none of these systems can be analyzed analytically, or at least it's very rare for that to be the case. And so you want to do experiments in which you do a simulation and you let that run for a certain period of time, but you want to know that the length of time that you run the simulation for is long enough that the system is in equilibrium, and the results that you're measuring are close to the equilibrium. And this connects extremely closely to the kind of analysis that we have for randomized algorithms. And so that fitted in very nicely. So we have this very nice interdisciplinary research theme, which is bringing together theoretical computer science, statistical physics, probability theory, and combinatorics. And I like the way that you can dip into all these topics. Right. So when I was a student, a PhD student at Edinburgh, what is now informatics was spread over a number of sites. And so computer science was situated in King's Buildings in a residential area to the south of the city. while artificial intelligence and machine intelligence and epistemics, I mean, it was were all in separate sites, in more in the centre of town. So this meant that computer science was in the same building as mathematics and physics. So I guess this provided a more suitable environment for the sort of studies I was making. This kind of fragmentation couldn't last, and so eventually I think the university insisted that all of these strands come together. And this was coincided with the construction of the forum. So being at King's Buildings was quite good from a scientific point of view, but just from the point of view of eating and the convenience of places to eat and stuff like this, then obviously being in town was better. Now everyone is together in town, and it's a nice environment, I think, that we've got now. So I left Edinburgh just the very year before the forum opened, so I never got to benefit from it myself. So as I said, I was studying the diploma in computer science, or MSc if you like, at Cambridge. I was interested in applying my mathematical interest to computer science, this new area. It seemed like a good thing to do. Cambridge at the time was not the place to do this, and I was recommended that I should go to Edinburgh, which was a fantastically good recommendation. When I got here, I discovered that the work in theoretical computer science was focused on the European-style program correctness, logic-based style of computer science. There was a small group interested in computational complexity and analysis of algorithms. And in particular, there was a very strong researcher, Leslie Valiant, who taught a course here on computational complexity. This really interested me, and so I decided I wanted to work on that for my PhD. And fortunately, he agreed to be my advisor for the studies, and so that gave me a fantastic head start in my research studies. And I think that there was some problem that he suggested to me at that stage. It may have been during the PhD or a little bit afterwards. I won't say what that problem is because that would be digressing too much. But it turned out to be a fantastic question because one way or another, it sort of kept me and several other people busy for the next 2 decades, actually, and got me into this train of studying randomized algorithms, in particular randomized algorithms based on the simulation of these mathematical objects called Markov chains. So I arrived in Edinburgh in 1978, got my PhD in 81, and was fortunate enough to get a low-grade lecturing job. So I think it was called demonstrator. I think it's a grade that doesn't exist any longer. But so I walked straight into that. So I was enjoying it at Edinburgh, and I therefore ended up staying 29 years eventually, I think. And well, I probably would have stayed longer, except for personal reasons. I decided to move back south again. So I've very much enjoyed this part of my life. And I think although computational complexity was always a minority interest at Edinburgh, nevertheless, there was a continuous small group working on the subject all the way through. So, I mean, like everyone else, I fall in love with the city. It's quite standard, I think. And so, I very much enjoyed the time. And it's good to see that Edinburgh is still, and the Department of Informatics is still flourishing the way it is. Yeah, so the stuff I've done hasn't, as far as I'm aware, had at this point direct impact on commercial or industrial operations. So it's more at the stage of, well, it's like mathematics in general. The stage we're at the moment is the sort of stuff I was studying for a PhD and in the earlier years of my career is now at the level that it can be found in graduate level textbooks, and possibly it's beginning to transfer to undergraduate textbooks. And so that's the kind of timescale and the route through which what we like to call these days impact occurs. So I think it's the impact is somewhat indirect and taking place over decades rather than years, I would imagine. But that's the stage we're at, and it's entirely plausible that whoever it is that studies with these textbooks will maybe not use these things directly, will be informed by them, and maybe have some that these ideas will have some expression in what's going on in the real world. So I was on the buses. This was a gap year. I guess it's not the standard gap year, but it did mean that as an undergraduate, I arrived at university with quite a stash of cash to keep me through the lean years. So it was. I wasn't driving. It was in a position which now doesn't exist. So the younger viewers won't know about it. A bus conductor who was the second person on the vehicle, just there to sell tickets and ring the bell and stuff like this. I mean, it was fun for a few months. I didn't have, but because I didn't have to do it for the rest of my life, that made it more pleasant, I think. So in my spare time, I guess one of the things I do is to make use of all the facilities, very numerous and varied, that London offers. Museums, galleries, whatever. And also, I enjoy getting out for walks. It's not quite as good a location as Edinburgh for this activity, but nevertheless, it is possible to get out far enough into the country to get some reasonably decent walking. So I would say those are the main things.